Greetings everyone, I'm Triet, a researcher from CREST at the University of Adelaide. I would like to present our MSR 2022 paper on the use of 5 vulnerable code statements for software vulnerability assessment models, co-authored with Professor Babar. In this study, we're the first to investigate the use of machine learning for function-level vulnerability assessment to provide timely information for vulnerability prioritization and fixing. As part of software development, developers face many vulnerabilities that can pose serious security threats. However, in practice, developers wouldn't have enough time and resources to address all of these vulnerabilities at once. Now a burning question arises: which vulnerabilities should developers prioritize to fix, as not all vulnerabilities are equally dangerous, and how to perform such prioritization? Recently, many studies have proposed data-driven methods to automate vulnerability assessment by predicting the CVSS assessment metrics from large-scale vulnerability reports in the wild. CVSS, or Common Vulnerability Scoring System, provides various metrics to quantify the exploitability, impact, and overall severity of vulnerabilities. In practice, all of these metrics are useful to perform thorough vulnerability assessment for prioritizing the fixing. However, there are several notable limitations with these vulnerability reports required for the current assessment techniques. Firstly, these reports don't usually contain the context of vulnerabilities, like nearby affected code, that are likely useful for vulnerability assessment. Secondly, such reports are mostly created manually, which is both time-consuming and prone to error. We also found that around 97% of the NVD reports with CVSS metrics were published 146 days on average after vulnerabilities had been fixed, which will significantly delay vulnerability assessment. Thus, an alternative approach is to use source code containing vulnerabilities directly for the assessment task. Here another question arises: how to perform code-based vulnerability assessment, specifically on the code function level, using the current data-driven methods. So here's a typical workflow of using machine learning to predict the CVSS metrics on the code function level. In this study, our investigation focuses on the input code functions, as there are different types of statements that can be used as inputs for machine learning models. First, we have vulnerable statements which directly cause a vulnerability in a function. These statements can be detected manually or automatically, and we hypothesize that they are likely more relevant and useful for vulnerability assessment than non-vulnerable statements. But we still need to test this hypothesis in research question 1. In research question 2 and 3, we investigate to what extent the non-vulnerable statements that may or may not be related to a vulnerability would affect the assessment performance. Here in research question 2, we combine context lines with vulnerable statements as a single vector input based on their code order. On the other hand, in research question 3, we treat them separately as 2 different vector inputs to give explicit information about vulnerabilities to the prediction models. Here's our experimental setup to answer these 3 research questions. First, we obtained vulnerable code statements from the modified lines in Java vulnerability fixing commits. We also considered 3 variants for extracting the code context. First, using param slicing. Second, using n lines surrounding vulnerable statements. And third, using all the other lines in a function. We used 6 contemporary code feature extraction methods alongside with 6 commonly used machine learning classifiers for predicting the CVSS metrics. We tuned and evaluated these models using tenfold cross-validation technique based on Matthews correlation coefficient MCC and F1 score, where MCC is the main metric as it considers all the cells in the confusion matrix. Now I will present and discuss our key findings. Here we'll focus on the MCC results as it's the main evaluation measure. The F1 score results can be found in the paper. For research question 1, we found that the models using vulnerable statements were 7.4% better than the ones using non-vulnerable statements, despite being much smaller in size. This result supports our hypothesis that vulnerable statements are indeed useful for the vulnerability assessment task. For research question 2, we show that all the contexts improved the assessment performance, in which using whole function resulted in the best performance. This is particularly interesting as it implies that we don't necessarily need to know the exact location of vulnerable statements in a function to develop effective assessment models. For research question 3, despite the intuition that double inputs would provide extra information about vulnerabilities to prediction models, we didn't find any significant performance improvement over the single input counterparts. And again, using whole function performed the best in the double input scenario. If you're interested in the optimal choice of feature extraction and classifier models for function level vulnerability assessment, please read our paper for detailed discussion. Here are the key takeaways of our study. We're the first to automate function level vulnerability assessments using machine learning to enable earlier vulnerability prioritization and fixing without waiting for vulnerability reports. Through extensive experiments, we found that the assessment models perform the best when using entire function as inputs. Overall, we provided the first yet promising baseline models for function-level vulnerability assessment, which hopefully would stimulate other future work to further advance this new task. If you're interested in our paper, please scan this QR code to read the preprint and visit the GitHub link for data and code. This also concludes my presentation. Thank you very much for your listening.